So today I'm going to talk about some issues that were not resolved by the last video. They're both about primes. I touched on both of them, but I didn't explain them fully, so I thought that this video, I could cover them more in detail to clear up any confusion. So I'm going to touch on two problems. The first is Euclid's proof, which I sort of skimmed over last time. It's very interesting, and I'll show you the proof this time and explain it. Secondly, I'm going to explain why we care so much about primes. I didn't fully explain that last video. I said that we cared about them a lot, but not that we, not why. And there is a good reason why they're important. So we're going to jump right into it and look at Euclid's proof. So Euclid's proof was made around 300 BC. It's a long time ago. Before that, they thought that there was a finite number of primes, but we know that is not true now. So, this proof says that lowercase p subscript 1 is the first prime, lowercase p subscript 2 is the second prime, and so on. And up to p sub r, which it's assuming that there's a finite number of primes, and that's the last prime. Capital P is the product of all the primes through P1 through PR, P sub r, all of them, and plus 1. So this is, we can write this formula, and p would have to be an integer because it's many integers multiplied by each other, and then you add 1. So that's the logic behind it. So if p, capital P, is prime, then we don't have a problem. That means that it's larger than PR, which means for every PR, there'll be a larger p. It gets more complicated, however, when PR is not prime. When capital P is not prime, sorry. So when this happens, then we have a problem, because it could just be a normal number, but as we see, then you'd have to be dividing 1 by an integer in an attempt to get an integer, and that just doesn't work. And I'll show that in a little while. So, as I write this down, Euclid's theorem is very interesting, and it's amazing that someone devised this so long ago. So, if P is not a prime, then we would have to be dividing by 1, and I'll show how. It's from a time where we were a lot less mathematically adept, and so it's very interesting that we figured it out at that time. So how does this work? So first we have to understand that capital P minus 1 is every prime goes into it, assuming that there's a finite number of primes. And therefore, so all primes multiplied together, this means that every prime goes into it. Every prime is a factor. So, as we can see, that means that P plus 1 is not. But it can't be. So, therefore we can conclude that P has nothing can go into it an even number of times. Because, think about it, when 2 goes into a number, it doesn't go into the next number. When 3 goes into a number, it doesn't go into the next number. That's true for all numbers except 1. So, if all the numbers go into P minus 1, which numbers, I'm talking about primes here, go into P itself. And remember that every non-prime number is composed of primes. Every number has its own prime factorization. So if any number but 1 goes into P minus 1, then it can't go into P, which is really an interesting proof, which shows that, in fact, P has to be prime, so it would appear. And well, that's not entirely true. It does mean that this proof still works, even if P isn't always prime. It still has to show that there's going to be a prime larger than PR for any value of PR, and so there always have to be an infinite number of primes. As I jump into the next part, I just want to say that was partially in part to Thomas K. Caldwell's article. So, why are primes so coveted? That's the second question that I'm going to answer. It's a good question. I touched on it last time, but not very well. And the answer is 2 words. It's industrial and encryption. So it seems strange, but I'll explain it. And that's most of the reason why primes are so important. So encryption, the idea is that I put a cipher on something that I'm trying to hide from people, and I send it, and then the person trying to steal it can't read it. So the basic premise of this is that one prime times another prime will always make a non-prime number, and that non-prime number will always have 2 factors. Its prime factorization will be 2 numbers, and they'll both be prime. These primes would be randomly generated, more than 10 digits long, often more than 100. They're very long primes, and they're generated by computers. So, say I want to send a message, then I would encrypt it with one of the primes. And then the only thing I would send I would send it in a public domain. Say a bank. I'm sending the product of the 2 numbers publicly. Everyone can read those numbers. They're hundreds of digits long, and I could pull it up on my computer if I wanted to. And so, yeah, the numbers are free. They're easy to access. But the thing is that it's extremely hard to factor out numbers in these primes. It's very, very hard. And so yeah, these numbers, they're actually visible to everyone. Banks use many different ones, and it's no secret. The secret is finding the factor. And only the bank would know that. And so that's the beauty of it, is that it uses these huge numbers to do something very simple, but make it nearly impossible to hack. And that's one of the reasons why primes are so big, and why if you can discover how to find out new primes, you'll, for one thing, really hurt banks' encryption, but you'll also be famous. But no one has. So, yeah, prime factorization is something that's taught to elementary schoolers for the most part. But it's so hard when there's huge numbers involved that computers have trouble doing it. And, well, it's quite easy to multiply 2 numbers by each other. It's very hard to find out what the original 2 numbers were. So that's why finding primes is so important. Thanks to the Berkeley source, which I'm going to post in the description, that was very helpful in making this video. So, thanks for watching. hope you enjoyed the video, and look forward to other math videos that I may be making in the future, and I'll talk to you later.